Hi, I'm Mike Wyrostek, the Director of Marketing at Hampford Research in Stratford, Connecticut. Today we're going to talk about azo dioxides and their use as inhibitors and retarders in photoinitiated cationic polymerization. UV adhesives absorb radiant energy from UV light and convert it to chemical energy, resulting in curing. A properly formulated system must exhibit long-term stability under normal storage conditions and undergo rapid polymerization once irradiation energy, either EB or UV, is applied. Inhibitors make up an important component of all UV curable adhesives. Active center chain addition polymerizations are generally strongly exothermic. Inhibitors are used to control the reactivity of monomers, avoiding runaway conditions. They also extend the storage lifetimes, making purification and transportation possible. Of particular importance is the stabilization of monomers in the presence of initiators. This is demonstrated in this simple graph. An inhibitor works by totally suppressing polymerization until it is consumed by the reaction. At that point, the polymerization rate proceeds at the same rate it would if there were no inhibitor present. A retarder functions by reducing the overall rate of polymerization, even though it begins at the same time polymerization would normally happen. Azo dioxides, such as Hampford's UVTS 52, have the unique ability to function as both an inhibitor and retarder. You can see this through simple opaque kinetic analysis. In this analysis, samples were prepared by sandwiching a thin film of liquid monomer containing the designated photoinitiator between two plastic sheets. The average thickness of the sample was 0.9 millimeters. Irradiation with UV light was carried out using a mercury arc lamp equipped with a liquid optic cable. A minimum of 3 kinetic runs were performed for each system to ensure reproducibility, and the temperature of the sample was monitored at a rate of 2 measurements per second. And you can see in the presence of the UVTS 52 both the time it took for polymerization to occur, indicating inhibition, was longer, and also the rate at which polymerization occurred, again indicating retardation, was also. As we increase the inhibitor from 1% to 2% to 3%, you can see the effect of inhibition increased. The time it took for polymerization to occur was longer, but it didn't function any more effectively as a retarder, that the rate of polymerization once it did occur remained fairly constant. Let's take a closer look how these unique molecules work. Azo dioxides have the ability to chelate the acid generated by the photoacid generator that produces polymerization. Here on the left you see the azo dioxide. The H3O represents the acid generated by the PAG, and you see here how the azo dioxide actually chelates the free acid, preventing polymerization to occur. When exposed to heat, the ring of the azo dioxides open up, giving its characteristic blue color. This also allows the release of the proton, resulting in polymerization. This is what gives azo dioxides their thermal reversibility characteristics. Here's the complete reaction mechanism. When exposed to UV light, the PAG releases a free acid. This in turn gets complexed by the azo dioxide, preventing polymerization. This is the inhibition step. When exposed to high heat, the azo dioxide releases the free acid, allowing polymerization to occur, and this is the thermal reversibility that we talked about. So next we wanted to look at this under more real-world conditions. So we made up a standard epoxy formula using common monomers and photoinitiators. Films were drawn down to a thickness of 0.8 mils and cured via a filtered fusion D lamp. It's important that the light is filtered, that the IR wavelengths are removed, because those produce heat, which in turn will take away the thermal reversibility aspect of the azo dioxide. The line speed varied anywhere from 10 to 47 feet per minute, and an aluminum block was used as a heat sink. Here's a list of some of the formulations that we used. OPPI, OPPI PF6 were two of the photoinitiators that we used. Those were selected because of their high activity. R2074 was also used as a photoinitiator. Some of the formulas included sensitizers, either ITX or 9,10-diethoxyanthracene, also from Hampford Research. And then we varied the concentration of inhibitor, the UVTS 52, anywhere from 1 to 2%. And what we found, it was this area where we got the best performance, using the OPPI as the photoinitiator, either ITX or 9,10-diethoxyanthracene as a sensitizer, and UVTS 52 at 2% as an inhibitor. We found at lower concentrations of UVTS that upon exposure to UV light, we actually did see some curing, and then when the concentrations of UVTS were higher or the system wasn't as active, meaning that the photoinitiator concentration was lower or the sensitizer wasn't present, that it lost the thermal reversibility aspect of it, that it prevented curing under UV light, but even when exposed to high temperature, it still didn't cure. You can see that here, that the top two panels are an epoxy formulated without the use of inhibitor, and you can see when exposed to UV light, they cured fully. Whereas in the presence of the UVTS 52, the epoxy didn't cure and it remained liquid even after exposure to UV energy. Upon heating, you see that even with the UVTS, the epoxy cured completely, demonstrating the thermal reversibility aspect. As a test, what we did was we took that same epoxy with the inhibitor in there, not exposed to ultraviolet light, but exposed to heat, and you can see that it still didn't cure. So it isn't the heat that's allowing the cure, it's the combination of ultraviolet energy followed by heat. Some of the other observations: formulas without azo dioxides exhibited normal cure properties. In all cases, formulations using azo dioxide material exhibited thermal reversible inhibition, remaining liquid after UV exposure and then polymerizing to a hard, MAR-resistant film after heating. As we discussed, too low a level of inhibitor resulted in a partial cure after UV exposure. Too high a level of the UVTS resulted in incomplete cure after thermal exposure. Formulations with more active PAGs exhibited better performance, and formulations incorporating sensitizers exhibited better performance as well, with the ITX generally outperforming the 9,10-diethoxyanthracene. The systems were very heat dependent. Exposure to heat and UV light simultaneously will result in polymerization. Again, that shows the importance of using filtered light. Azo dioxide should be used at the lowest effective concentration. Too high a level will result in inhibition without the thermal reversibility. Too low a level will result in poor inhibition characteristics. Post-UV curing is a function of both time and temperature. Higher exposure temperatures resulted in shorter curing times. You can see at over 100 degrees C, it required less than a minute to initiate curing, where at the lower temperatures, 60 to 65 degrees centigrade, it took 5 minutes or more for the system to cure. What's interesting is the entire area does not need to be exposed to the high heat, only a small amount of the epoxy. That the polymerization, the exothermic characteristics of polymerization generate enough heat for it to become autocatalytic and continue to cure, giving very deep cure characteristics. Some of the potential applications for this type of system: photoactivated adhesives, structural applications, electronics, toys, appliance assembly, room temperature pot life stabilizers, particularly important for the 3D printing industry, and light stabilizers to protect the coating resin from photochemically producing free radicals and breaking down. So in conclusion, inhibitors make up an important part of UV curable adhesive formulations. Azo dioxides have the unique ability to act as a thermally reversible inhibitor, and the incorporation of these type materials offer significant commercial opportunities. Thank you for agreeing to spend a few moments with us learning more about azo dioxides and their use in epoxies. For more information, please visit www.hampfordresearch.com.